Good morning, everyone. Thank you for joining my talk. My name is Soumya Sampit Mahapatra, and I'm an application developer at Additive in Friedrichsdorf, Germany. I'm going to give a talk about MetalLink. It is a package that I initially started as an experiment, and over the time, I've been trying to expand it. It is still under development, and I hope to release it as a packlet before the end of this year. The main reason that I got into developing this is because about a year back I needed to run some complex computations and there was no way to run it faster with Mathematica on my Mac. The new Apple Silicon Macs no longer support CUDA computations. I tried playing around for a while with OpenCL but soon realized that it doesn't use the full capabilities of the GPU hardware on Mac. And furthermore, Apple itself has dropped support for new versions of OpenCL. So I started researching the Metal API. So here is an overview of the different topics that I am going to cover in this talk. I will begin by introducing the Metal API itself. I will briefly talk about the architecture, some common terms and the similarities with the CUDA and OpenCL APIs, the feature set that is provided by Metal. I will also then discuss the compute workflow in a bit detail. It is a bit complicated, but I have tried to oversimplify the things for the scope of this presentation. And also it is very different from the workflow used in CUDA because there is no bottleneck of transferring the data from system memory to GPU memory. Apple uses a unified memory structure and both the CPU and GPU have access to the same memory. Then I will go into the development details, the different strategies that I have used throughout the development and the various different decisions that I had to make in order to make the framework consistent and coherent. And finally, I'll show a few demonstration examples of doing computations on the GPU. So what is Metal? Metal is a graphics and compute API that is developed by Apple, mostly for Apple hardware. I say mostly because Metal can actually be used with hardware from other manufacturers. I tested these functions with an NVIDIA card and it worked, kind of worked. Some of them worked, some of them didn't work. So I would say that it is not optimized for other hardware. Metal also includes its own shading language called the Metal Shading Language, or MSL for short, which is used for writing the compute kernels. It is a variant of C++ and it is very similar to CUDA. And since it is natively designed for Apple, it has extremely low overhead. About the hardware, the Apple Silicon chips come with integrated GPU, that is the GPU sits directly on the chip and it shares the unified memory along with the CPU. The GPU core count is different for all machines and it ranges from 7 on the base models to 64 on the higher end. Apple has slightly different definition for GPU core count from other manufacturer. In case of Apple, each core is split into 16 execution units and each of which is further split into 8 arithmetic logic units. In case of other manufacturers, the core count usually refers to the arithmetic logic units directly. By that comparison, a higher end model in Mac would have about 8,192 compute cores. And like I said, the memory is unified in this case, and both CPU and GPU have access to the same memory. Additionally, the GPU also has some extremely high-speed cache memory, which are very useful. The Metal Shading Language comes with some notable features. For example, it has got special data types to deal with images and textures. It has also got built-in atomic data types that take care of data synchronization and race condition between the threads. The Metal API also includes metal performance shaders. These are built-in highly optimized kernels for several operations. They have optimized solutions for tasks like linear algebra, Fourier analysis, image and video processing. And further built on top of the MPS is the MPS graph, which is a library for performing neural network training and inferencing on the GPU. So yeah, we can see that Metal API has got lots of features and they're just waiting to be translated and used from Mathematica. Now, I would like to outline the general workflow for performing parallel computations on the GPU. The first step is to create a compute kernel, and it is also known as the shader. We use the metal shading language for this part. In this example here, the kernel performs a parallel addition of two arrays. The function takes 4 arguments, 2 arrays that contain the input data, a third array that is used to store the result, and the final argument is an index with a special keyword called thread position in grid, which passes the 2D coordinates of the threads in the grid. I will explain about this shortly. The function itself just has a single line of code that tells to add the 2 values at index and store it in the result variable. With the kernel prepared, we shift to utilizing the APIs, using which we push the kernel and the data to be operated upon to the GPU. The Metal API is provided through the Metal framework, and every operation in the framework is done through the Metal device. Therefore, the first step is to create a reference to the Metal device. This initializes the device object in the heap and provides access to all the properties and methods associated with it. Once the device is initialized, a library is created into which we load all the kernels. One of the good things about Metal is that the kernels are loaded at runtime and get compiled just in time of execution. In practical cases, a library would consist of several kernels. However, for any specific computation, only one kernel would be required to pass to the GPU. This is done by referencing it through a pipeline state object. The next requirement is the command queue. The command queue is where all the following operations are carried out. The creation of Metal device, the library, and the command queue are expensive operations, but they are also reusable objects. Therefore, they can be initialized just once. Now, with the command queue ready, we create data buffers and load input into them, and also create empty buffers to store the results. Then we create command buffer, using which we create a command encoder. The command encoder is used to encode the pipeline state object, the data buffers, and any other instructions, and push them into the command buffer. An important detail at this stage is to compute the organization of threads and thread groups. The equivalent terms for this in the CUDA and OpenCL world would be work and work groups. I will explain how to organize them in the coming slides. Finally, after encoding, the command buffer is committed. This operation delegates the encoded instruction to the GPU. That is, this is where the code is about to get executed in the GPU. In case of a synchronous workflow, a wait command is passed that locks the program until the GPU returns the result. In case of asynchronous mode, a callback function is specified that is carried out whenever the GPU returns any result. For the scope of this presentation, we restrict ourselves only to the synchronous mode of operation. The command queue, command buffer, and the command encoder can be a bit tricky to understand and can be confusing too. It was the case for me when I was trying to understand them. Therefore, I find this picture which compares them to a railway system very helpful. This is an AI generated image with a few modifications that I did to add the keywords. The railway track can be equated to a command queue because it's like a queuing system where all the trains go through. Then the command buffer can be equated to the cargo itself because it's got a specific structure into which we have to put in the commands. And finally, the cargo loader can be equated to the command encoder because it loads the commands from one point and fits them into the buffer in a specific organized way. An important step that needs attention is the organization of threads and thread groups. Kernels are executed over a grid of threads, and each thread represents a single instance of the running kernel. The threads are addressed globally using the attribute thread position in grid. As it can be seen from the image here that the indexing begins from the top left corner of the grid, as in the case of matrix or image coordinates. The grids can be one-dimensional, two-dimensional, or three-dimensional, and it depends on the task. In this grid, the thread at this position is indexed using the coordinates 9, 10. Similar to threads, we have thread groups. Threads are organized into thread groups. Thread groups are a group of threads that execute a kernel function together, and they share a common block of memory. Kernels run independently, but they are capable of collaborating within a thread group. This is really helpful in case of kernels that take diverging paths across threads. However, it is usually advised to not use any if statements inside kernels, as very often they lead to race conditions. Threads inside a thread group are indexed relative to the origin of the thread group and can be obtained with the attribute thread position in a thread group. As shown in the image below, the blue block is a thread group, and the tiny red block here belongs to the thread group, and this particular thread is addressed with respect to the thread group, and its relative position is 1, 2. So with this understanding of threads and thread groups, let's now see how we can compute them for a given task. As an example, let's say we want to do some processing with an image. Each pixel on the image gets a thread that runs an instance of the kernel on it. This means that the number of threads will be simply equal to the number of pixels on the image. Now, for the given number of threads, we need to compute the optimal number of thread groups. This depends on two important constants. The first one is the maximum number of total threads per thread group, and the second one is the thread execution width. The maximum total threads per thread group is sufficient in case of 1D computations. However, we require the thread execution width in case of 2D computations. These values get calculated when a pipeline state object is created, and they remain constant throughout the program. For my machine, the maximum total threads per thread group is 1024, and the thread execution width is 32. For the 2D example that we have considered, in case we want to compute uniform thread group sizes, we do the following. In order to get the thread group width, we set it to the thread execution width, which is simply the maximum width possible. For the thread group height, we divide the maximum total thread groups possible with the thread execution width, so that it equally distributes the threads over the thread execution width. Then we calculate the number of thread groups possible by scanning the thread group span over the image. So on the width axis, we get the total number of thread groups by taking the image width and adding an extra thread group width, dividing it with the image width, and we do the same operation for the height as well. The extra addition we do for the thread group width and height is to compensate in case the image is not a multiple of the thread group dimensions, and this results in uniform thread group sizes. Finally, these thread groups are dispatched using the dispatch thread group API. However, since the thread groups become uniform, if the image is not a multiple of the thread group dimensions, we get some unused threads along the edges of the image. And this often results in unused kernels, and therefore we need to specify an early exit condition in the kernel itself. The underused kernels may provide suboptimal performance if there are no proper early exit conditions defined on the kernels. As an alternative, Metal provides an option to dispatch only the threads over the grid, and it takes care of computing the thread groups automatically. In this case, it computes the thread groups of non-uniform dimensions along the edges to perfectly wrap the image. And in this case, there are no unused threads. This also means that we don't have to write any early exit conditions in the kernel code. Now, I would like to talk about the different development strategies that I went through in different phases of this project. I started with WSTP, the Wolfram Symbolic Transfer Protocol, because it was fairly easy to set up and do some quick tests with the concepts. But I realized that with WSTP, the external functions do not share the kernel's memory space, and therefore there was data transfer involved, and this kind of defeated the purpose of parallel computation. So I further carried out the experiment with LibraryLink. With LibraryLink, it is possible to load external functions directly into the Wolfram's kernel memory space. The external functions must conform to a certain signature, and it is only possible to create the external functions in C or C++. Metal's APIs are available in Objective-C and Swift. And Objective-C can be interspersed with C code because it is just an extension of C. However, the code becomes quite cluttered, and also for simple tasks, the number of lines of code exceeds 50 to 100, and therefore as the code base grew, it became very difficult to manage it with LibraryLink. Another problem with writing in Objective-C is that the documentation does not cover a lot of newer functions, and only the Swift variant is written. Therefore, the next logical move for me was to explore Swift functions and somehow integrate it with Mathematica. And I come up with the idea of Swift plus C bridge, where the APIs are written in Swift, and there is an intermediate bridge written in C using the LibraryLink, and through it, the Swift side is interfaced to Mathematica. But in this case, there are lots of points of failure, and I had to jump around between multiple frameworks, and also there is no bidirectional referencing, and therefore I had to drop this idea. At this point, I came across the foreign function interface in Mathematica, and by far this has provided the most flexible solution for the development strategies. What I do in this case is that I write the wrapper for the Swift APIs and use the attribute C declaration to expose them to C-style languages. And then it is possible to load this function directly using foreign function load into Mathematica. And this makes it possible even to expose the lower level APIs into Mathematica and do most of the development directly in Mathematica. However, a couple of caveats in this case is that there is slightly increased overhead during the function calls, and it requires some degree of manual memory management. However, this is all doable from Mathematica. There is one more solution available to us. It's the Metal C++. It is a low overhead C++ API written over the Metal language, and it makes it possible to develop everything in C++. Unfortunately, at this point, it is not very well documented, and therefore I have kept it only for special purposes in case I require it in the future. So finally, we are at the most interesting part of the presentation. Here I give some demonstration and talk about the results. Most of the results have been pre-computed because they are computationally and memory-wise very intensive. The first function is simply the metal device information. When evaluated, it gives some basic information about the device present. In my case, it is an Apple M2 device with about 11 gigabytes of memory. The memory type is unified and the maximum buffer length available is about 8 gigabytes. The data transfer rate is 0 because the memory type is unified and virtually there is no kind of memory transfer involved. I've got a couple of basic functions. One is metal map. It is very similar to CUDA map, and like CUDA map, it supports these 15 functions. I have done a comparison of computation times in the CPU and the GPU. For the computation, I've just taken the sine function and mapped it to arrays of different length. The length ranges from 10 to the power of 1 up to 10 to the power of 8, which roughly translate to 100 million. And as we can see from the plot here, the computation time between the CPU and GPU is quite similar, except in the case of 10 to the power of 8 array length, where the GPU is slightly faster. I have done a similar comparison with MetalAdd that adds to one-dimensional arrays. And in this case also we can see the computation time is quite similar for the case of CPU and GPU, and only in the case of GPU for array length of 2 to the power of 8, it is a bit faster than the CPU. The reason why we see this is because the kernels are not very optimized, they are handcrafted. And also when doing computation on the GPU, there is some time taken due to the buffer allocation. And most importantly, the CPU evaluation is done in 64-bit precision, while Metal currently supports only up to 32 bits. And also the operation mode is synchronous, which means that the GPU kind of does the complete computation before it can send back the result. If we transition to asynchronous mode, the GPU can send back intermediate results, and this provides a significant boost. The next demonstrations that I've got here are related to matrix operation, and I've created two metal matrix operations, matrix add and metal matrix multiply. In the first case here, we are adding a list of matrices. Each matrix is of dimension 1000 by 1000, and we are adding 1000 of those. So adding all these matrices on the GPU with metal matrix add takes about 4.7 seconds, while on the CPU it takes about 37.2 seconds. Similarly, in the case of matrix multiply, in this case I'm just multiplying two large matrices. Each of them have 10,000 rows by 10,000 columns. On the CPU it takes about 11 seconds, while on the GPU it takes 1.7 seconds. So it's roughly about 6 times faster in the case of GPU. So in case of the matrix operations, I've used MPS matrix data type from the Metal API under the hood, which is very efficient at storing large matrices and performing matrix operations. And therefore, we see a significant boost in performance in the matrix operations. I am currently working on developing the matrix decomposition techniques. By developing, I mean that I'm just translating the Metal API into Mathematica, and similarly for eigenvalues. The next demonstration is a Monte Carlo simulation for the estimation of pi. What it does is it generates a set of random real numbers with two coordinates within the range -1 to 1, and it counts the number of points that fall within the unit circle and multiply them by 4 to get an estimate of pi. With this computation on the CPU, it takes about 14 seconds. I have done the same computation with multi-threads on the CPU, and the computation time reduces to about 2.9 seconds. And finally, the same computation on the GPU comes down to 0.8 seconds. In order to do the computation on the GPU, I have written three functions. One is metal random matrix, which generate random coordinates using metal. Then there is metal norm, which computes the norm of these coordinates. And metal count counts the values of norm whose absolute value is less than 1. The final demonstration is using image processing, and for this I have written a Gaussian blur function in metal. In order to test this, I have taken this example image of Morocco. This is a fairly large image and has a high resolution, therefore it's a good candidate for stressing the GPU. The plot here shows the computation time when performed on the CPU versus the GPU. For the CPU computation, I have used the Gaussian filter function, and for the GPU, I have used the metal variant. The x-axis shows the radius of the kernel, and it's in the order of 2 to the power of 2 and goes up to 2 to the power of 9. For smaller kernels, we can see that the CPU performs a bit faster, but as the kernel size increases, we see CPU consumes more time, while GPU throughout remains constant, relatively constant. The slow computation for smaller kernels in case of GPU is primarily because of the buffer allocation and slight overhead due to the foreign function load. Other image processing functions that I'm currently developing are the histogram equalization and generic convolution and Laplacian filters. So that brings me to the end of my presentation. Thank you everyone for being here at my talk. And if you got any questions, feel free to ask. So I see there are a few questions. I'm going to read them one by one and try to answer. So the first question is, do you think it would be better if Apple made a metal shading language for Swift rather than variant of C++? I think there would be pros and cons for this. From a development perspective, it would be definitely easier because everything would be more coherent and consistent. But yeah, that would slightly impact the performance, I think so. Does the execution unit in an Apple GPU have its own instruction stream? Would you say that the SIMD width of Apple GPU is 8 because there are 8 ALUs per execution unit? No. In case of Apple, the SIMD is defined as the thread execution width itself, which means that 32 threads get executed and they run the same kernel at the same time. And the next question is, where can we get this backlit? I have not yet made it public. I'm still working on it. I hope to release it by the end of this year. Next question is the last plot of a presentation, in the last plot of a presentation, why was the CPU faster for an exponent of 8 than 7? Like I said, I think it's probably because of the foreign function overhead, and yeah, the functions are not yet still optimized. I have to still work on them a bit. There is much more room for improvement, and also when I include the asynchronous mode of operation, it will be much faster in that case. Is there a preview version of MetalLink available? Not yet. I hope to release it soon. I'm just still working on it, and I'm doing a bit of code cleanup, and yeah, it will be made available soon. And there's one more question. When you compared the speed of Apple's CPU versus GPU, did you use Apple's Accelerate library for the CPU? No, I did not use Apple's Accelerate library, although that would be a much more fair comparison in this case. I just used Mathematica's CPU version of the functions to do the comparison. Okay, I see no more questions. I guess that's it then. Thank you everyone for being at my talk.